A perfectly intact glass door sits completely undisturbed. Then, in a fraction of a second, it erupts into hundreds of thousands of tiny fragments. No impact, no warning. We understand how physical materials are supposed to fail. A baseball strikes a window, the force exceeds the material's limit, and the pane cracks. Action requires an equal reaction. Yet security cameras around the world routinely capture a very different sequence of events. Storefronts, shower doors, and balcony railings spontaneously turning to dust in completely empty rooms. If absolutely nothing touches the pane, where does the kinetic energy to destroy it come from? The force tearing these structures apart doesn't come from the outside. The source of the destruction is baked directly into the chemistry of the glass itself. Modern cities are wrapped in glass. We build sheer faces of transparent material hundreds of feet in the air, trusting them to hold back the wind, weather, and gravity. To accomplish that, engineers rely on a specific variation of the material, tempered glass. By altering the physical structure during manufacturing, they create a pane up to 4 times stronger than standard glass. That strength makes it the default safety barrier for nearly every high-risk application you encounter daily, from the windshield of your car to the observation deck of a high-rise. But the engineering process that generates this massive physical resilience introduces a permanent hidden flaw. The exact mechanism keeping the window intact is the same mechanism waiting to tear it apart. The cycle begins in an industrial furnace. Sheets of standard glass are subjected to extreme heat, pushing the material well past 1100 degrees Fahrenheit until it becomes soft and malleable. Then comes the crucial step. The red-hot pane is immediately blasted with high-pressure cold air. This rapid cooling creates a severe temperature difference across the thickness of the pane. Inside, sudden cold air causes the exterior to rapidly shrink and compress. The hot inner core stretches as it cools. The glass solidifies, trapping a permanent tug-of-war. The exterior constantly squeezes inward. The interior pulls outward, storing immense mechanical energy. Most of the time, this extreme internal pressure holds perfectly steady. The window looks entirely normal, holding its shape quietly for days, months, or decades. But all that stored energy is highly volatile. A microscopic impurity left over from the furnace, or a tiny, nearly invisible scratch on the surface, can disrupt the balance. The entire pane sits in a constant state of internal war. If even a fraction of a millimeter gives way, the equilibrium collapses. When that tiny defect finally shifts, the glass loses its grip. The tension instantly snaps. The immense energy trapped inside since the day it left the furnace suddenly has a path to escape. The material cannot slowly crack to relieve the stress. The opposing forces tear through the entire structure simultaneously, blowing the glass outward in a sudden shockwave. The brutal irony? Manufacturers designed it to fail this way. Shattering instantly under high tension, it disintegrates into small, dull pebbles instead of deadly shards. Spontaneous breakage looks like a sudden, unexplainable accident, but the physics prove otherwise. It is the inevitable release of kinetic energy that was deliberately packed into the frame. The break was not sudden. It was already inside.